Okay, so in this video, this is a second video introducing you to the logic of hypothesis testing. In the first one, we saw how you could use the central limit theorem, normal distribution for a sampling distribution, and essentially compute a z-score to figure out the probability that a particular sample comes from a population. We're going to do the same thing for a two-group kind of experiment. And one thing that I left off in that other video that I realized that I left off is that there's one little caveat in that we have our z is going to equal. Actually, let me use the pen. So we're going to use our sample mean, right? And we're subtracting it from the population mean mu, and we were dividing by the population standard deviation. But actually, when you're dealing with a sampling distribution, you have to adjust this by how much you've sampled, or the square root of n, in this quantity here. It's called standard error of the mean. So our z's are actually the measure of variability here is standard error of the mean, which is standard deviation divided by the square root of n over that ratio. And so we're going to apply that same logic here with a two-group sort of situation. This would be a one-group sort of situation. So actually, let me get rid of that. And so what we're going to do, though, is we're going to use for our denominator in our statistic, we're still going to use standard error of the mean, but we're going to consider standard error of the mean for both our groups. And what we'll do is we'll sort of add it together. And how this gets calculated, you'll see, will vary depending on the formulas that we do. The T, the F, the Z tests all use some version of standard error of the mean, where we use the standard deviations in these groups together. We combine it to estimate the variability of our sampling distribution if we were drawing from the same population over and over again. And then what we're going to do also is, not because we have one group, but we actually have two groups, we're going to focus on the difference between our groups. And in particular, we could generate a mean for our control group here, right? And we could generate a mean for our experimental group, right? And the focus of interest could be on the difference between these means, right? It's just subtracting them. Now, consider, for example, that our experimental manipulation does nothing to behavior. Well, if we did this, the relative difference between these control and experimental groups, there's going to be some differences if we kept sampling over and over again, but it would hover right around zero, right? Because we've done nothing different to those groups. So that means that our mean of our sampling distribution would tend to be zero. That's supposed to be a zero. Would hover right around zero. Sometimes it'll be a little bit more, sometimes it'll be a little bit less, depending on which group has a greater mean, right? But it's all going to be hover right around there. And we can still apply that same logic, though, that, when I say most of the time, so plus or minus 2 standard deviations would capture 95, a little more than 95% of the sampling distribution. So we know that the vast majority of the time, they're going to fall, the difference in means is going to fall in here, and we can use our standard error mean to estimate the variability, right? So just like when we computed a z-score and we put it in standard deviation units, we're going to do the same thing there. So what happens is the focus becomes on the difference in means, right? So we take this mean of this control group and we subtract from it the mean of the experimental group, right? And it focuses us on two pieces of important variability, and essentially what we're doing is we're trying to see, is this larger than the denominator by a factor of more than 2? If it is, then, well, it's unlikely to be drawn from the same population, right? So that brings us to two sources of variability here. One is the source of variability, which produces the difference in our group means. And this is what's due to the independent variable. It's whatever we've done differently to the experimental group versus the control group, right? But there's another source of variance, right? And the other source of variance here are our individual subjects. So subject 1, subject 2, subject 3. They're going to differ from one another. And then, we might have subject 4, subject 5, right? And so on. Our subjects in the control group are not all going to have the same score, right? They're going to vary a little bit from one another. And the reason they vary from one another is due to all of those things that we don't understand or know. Maybe it's genetics, maybe it's their mood, maybe it's all those things that were uncontrolled. So we could say uncontrolled variables, right? Subject variability of all kinds. So that's the stuff that gets estimated actually down here. This is the stuff that we don't know in a particular experiment what is causing it. And because we don't know what is causing it, it gets treated sort of as error variance, right? So this is what we mean when we compute our test statistics, and whether it's a Z or a T or really even an F, we have two sources of variance, right? We're going to have the source of variance, which is due to our independent variable, right? And that goes in the numerator. And then we have a source of variance, which is due to really all the uncontrolled variables. So we call this the error variance, right? It's error in the sense that we can't explain it, right? Intersubject variability, right? And so we have this variance, which is due to our IV and error variance, right? And this is what we would commonly refer to as the good variance, right? This is what we're isolating. We're hoping to isolate as researchers. We think our independent variable does something, hence the name good, versus the so-called bad variance, right? This is the variance that we haven't controlled, that we don't know what's causing it, right? The so-called bad variance. Now, I want to emphasize something real quick. If you study individual differences, you might be focusing on this bad difference. That is, what is causing these people to react differently to the experimental context? And you might be attempting to isolate. But in a typical study in psychology, we're trying to minimize this bad variance through careful research techniques that we've discussed in the class, and good design and good sampling, etc., to minimize this bad and isolate the independent variable variance. But our statistics essentially are estimating this ratio. So if the ratio is large, right? If the ratio is large, it's going to fall out here, right? It's going to be rare or unlikely that this, if it's large, unlikely that difference would happen due to sampling. Maybe I should type it up. Unlikely to be caused by sampling variation, right? And that's in effect what we're doing with our statistics, is we're finding out, is it likely due to sampling variation? If it is, we're going to accept the null. If it's unlikely due to sampling variation, we reject the null. Right? That's the idea behind all of our statistics, is we're simply assessing how likely this would be to get the sampling variation. Remember, we're assuming that we haven't done anything, and so we're assuming that it is just sampling variation unless we have evidence to sort of reject that notion. So that's what we're doing. What we will do is, in future videos and in the class, is turn that logic into an actual formula.